in the quiet vacuum of space, 3I Atlas just did the unexpected. 4 months. Astronomers had tracked this interstellar visitor with a methodical precision that defines modern space science. Its trajectory was calculated, its velocity measured, its approach to perihelion mapped with mathematical certainty. The predictions were solid based on gravitational mechanics that had been tested and refined over centuries of observation. Then, on October 7, 2025, something changed. The deviation was subtle at first. A few observatories reported position measurements that didn't quite match the predicted ephemeris, the calculated positions where the object should appear at specific times. Initially, researchers assumed measurement error, atmospheric distortion, calibration, drift, or simple human mistakes in data reduction could easily account for small discrepancies. But as more observations accumulated from telescopes worldwide, a pattern emerged that couldn't be dismissed. 3I Atlas wasn't where it was supposed to be. The deviation exceeded observational uncertainty by statistically significant margins. This wasn't noise in the data. This was signal. The object had changed its trajectory. NASA's Center for Near-Earth Object Studies, responsible for tracking potentially hazardous asteroids and monitoring unusual solar system visitors, began intensive analysis of the discrepancy. Teams at the Jet Propulsion Laboratory ran orbit determination software using the complete observational dataset spanning from discovery in July through the most recent October positions. The results were unambiguous and deeply puzzling. 3.1 Atlas had experienced what astrodynamics experts call a non-gravitational acceleration, a change in velocity that couldn't be explained by the gravitational influences of the Sun, planets, and other massive bodies in the solar system. This wasn't unprecedented. Comets routinely experience non-gravitational forces through outgassing, the rocket-like effect created when sublimating ice jets material preferentially in one direction. But the magnitude and timing of 3I-ATLAS's deviation didn't match standard comet outgassing models. The numbers told a story that defied easy explanation. Preliminary analysis suggested the object had altered its velocity by approximately 0.3 millimeters per second, a tiny change by terrestrial standards, but enormous in the context of precision orbit determination. Over the weeks since perihelion, this small velocity change had accumulated into a position error of several thousand kilometers relative to predictions. To understand why this matters, consider the precision involved in modern astronomy. When professional observatories measure the position of a distant object, they achieve accuracies measured in fractions of an arcsecondangular measurements so small that they represent distances of mere hundreds of kilometers. At 3I-ATLAS's range from Earth, when an object appears thousands of kilometers from its predicted position, it means something real has altered its trajectory. Dr. Davide, a navigation engineer at JPL who specializes in orbit determination for asteroids and comets, issued a cautiously worded statement acknowledging the anomaly. We're observing behavior in 3I-ATLAS that doesn't conform to standard dynamical models. The object appears to have undergone acceleration that exceeds what we'd predict from outgassing alone, given its observed activity, level, and estimated mass. That last qualifier, given its observed activity level and estimated mass, contained layers of uncertainty that researchers were only beginning to unpack. Activity level question was straightforward but problematic. Spectroscopic observations and brightness measurements provided estimates of how much gas and dust 3I Atlas was producing. These observations showed moderate activity consistent with a comet that had survived perihelion and was gradually declining in brightness as it receded from the Sun. Nothing in the visible activity suggested the kind of vigorous, asymmetric outgassing that would be required to produce the observed trajectory change. The mass estimate was even more uncertain. Without knowing the exact size and density of the nucleus, calculating the object's total mass required educated guesses based on brightness, assumed albedo reflectivity, and typical comet density values. If 3IA TLAS was significantly less massive than estimates suggested, perhaps due to an unusually porous, low-density structure than the observed, outgassing could potentially account for the trajectory deviation, but that explanation required the object to be extraordinarily fluffy, essentially a gravitationally bound cloud of ice and dust with density approaching that of smoke. While some comets do have remarkably low densities, measurements from spacecraft that have visited comets suggest typical values around 400–600 kilograms per cubic meter, far denser than required to reconcile the observed acceleration with visible outgassing. The European Space Agency's Near-Earth Object Coordination Center issued its own analysis, confirming JPL's findings while adding additional technical detail. Their dynamical models showed that the trajectory deviation began approximately 2 weeks after perihelion passage, around mid-November 2025, and had been continuing at a relatively steady rate since then. This timing was significant. If outgassing were responsible, one would expect maximum effect during perihelion when solar heating peaked and sublimation rates were highest. Instead, the deviation appeared to strengthen as the object moved away from the Sun, and overall activity declined the opposite of what comet physics would predict. Amateur astronomers, following the story on astronomy forums and social media, began proposing explanations ranging from plausible to wildly speculative. Some suggested the object was venting gas from subsurface reservoirs exposed during perihelion heating, a delayed outgassing effect that could produce asymmetric thrust. Others proposed that 3I Atlas had fragmented, with undetected pieces altering the apparent position of the brightest component. More imaginative explanations ventured into territory that made professional astronomers uncomfortable. Could the object be artificially propelled? Might it be an interstellar probe from another civilization, executing course corrections as it surveyed our solar system? The similarities to Oumuamua, first confirmed interstellar visitor in 2017 that also displayed mysterious non-gravitational acceleration, were impossible to ignore. Harvard astronomer Dr. Avi Loeb, who had proposed that Oumuamua might be an artificial object based on its unusual properties, weighed in on 3I Atlas with characteristic boldness. When we see objects behaving in ways that don't match our models, we have two choices: assume our models are incomplete, or consider that we might be observing something our models never anticipated. Natural explanations should always be exhausted first, but we shouldn't dismiss possibilities simply because they make us uncomfortable. The scientific establishment responded with predictable caution. Press releases from NASA and ESA emphasized that natural explanations remained most likely, that additional observations were needed to refine trajectory models, and that premature speculation wasn't helpful. The message was clear: don't panic, we're still gathering data, and extraordinary claims require extraordinary evidence. But behind the measured public statements, researchers were privately puzzled. Informal discussions at conferences and in email chains revealed genuine uncertainty about what mechanisms could be driving 3IA TLAS's behavior. The object was operating in a regime where observational constraints were poor and theoretical models were sparse. The implications extended beyond pure astronomy into practical concerns about solar system monitoring and planetary defense. If objects could alter their trajectories through mechanisms we didn't fully understand, it compromised our ability to predict future positions and assess potential impact risks. While 3IATLAS posed no threat to Earth, its trajectory kept it comfortably distant. The principle mattered. Accurate trajectory prediction depended on understanding all the forces acting on an object. As October surrendered to November and 3I Atlas continued moving outward through the solar system, the astronomical community mobilized resources for intensive follow-up observations. Major observatories allocated telescope time to obtain high-resolution images, detailed spectra, and precise positions that might illuminate the cause of the anomalous acceleration. The race was on to solve the mystery before 3I Atlas faded beyond detection, carrying its secrets with it into the cosmic dark. The first comprehensive analysis arrived from the International Astronomical Union's Minor Planet Center on November 12, 2025. The technical report, designated MPEC 2025 V38, contained 47 pages of orbital elements, observational residuals, and dynamical modeling results that painted a picture both precise and profoundly unsettling. 3I Atlas had deviated from its predicted trajectory by 4,830 kilometers over a 23-day observation arc. The deviation was increasing at an approximately linear rate, suggesting ongoing acceleration rather than a single impulse event. The direction of acceleration pointed roughly 35 degrees away from the Sun, neither directly sunward nor anti-sunward, but at an oblique angle that didn't align with any simple outgassing geometry. Dr. Matthew Holman, director of the Minor Planet Center, summarized the findings in language stripped of technical jargon but heavy with implication. We're observing sustained acceleration that cannot be reconciled with standard comet models given the object's observed properties. Either our understanding of the object's mass, structure, or activity is significantly wrong, or we're witnessing a process that doesn't fit current theoretical frameworks. The report triggered immediate response from research groups worldwide. Within 48 hours, 3 independent teams had published their own analyses using different observation data sets and modeling approaches. All reached the same fundamental conclusion: something was pushing 3I Atlas in ways that standard physics couldn't easily explain. The numbers themselves were startling in their precision. Radar observations from the Goldstone Deep Space Communications complex had measured the object's radial velocity, its speed toward or away from Earth, with accuracy of millimeters per second. These measurements, combined with optical astrometry tracking the object's position against background stars, constrained the trajectory to unprecedented precision. The acceleration vector pointed at right ascension 245.3 degrees, declination minus 18.7 degrees, coordinates in the sky that corresponded to no obvious reference point. It wasn't pointing toward any massive planet that might provide gravitational explanation. It wasn't aligned with the object's rotation axis as measured from light curve variations. It simply pointed in a direction that seemed arbitrary from a dynamical perspective. This arbitrariness troubled researchers more than any specific characteristic. Natural processes tend to follow symmetry's gravitational acceleration points toward massive bodies. Radiation pressure points away from the sun. Outgassing jets align with surface features and solar heating patterns. The acceleration affecting 3 IATLAS followed none of these patterns. Dr. Danica Remy at the Harvard-Smithsonian Center for Astrophysics led a team investigating thermal models that might explain asymmetric outgassing. Their analysis required the nucleus to have an extremely elongated shape, something like a spinning cigar with active regions concentrated on one end. As this elongated nucleus rotated, the jets would fire in different directions, but over multiple rotation periods, they would average out to produce net thrust in a specific direction. The model was physically plausible and had been successfully applied to explain non-gravitational forces on solar system comets. But when Remy's team attempted to fit it to 3 IATLAS's observed behavior, the required parameters strained credibility. The nucleus would need to be spinning with a period of approximately 5.2 hours faster than most comets and have at least 80% of its active area concentrated in a small region on one end. It's not impossible, Remy explained in a video conference call with colleagues, her screen sharing showing thermal simulation results. But it requires a very specific geometry that we have no independent evidence for. We're essentially tuning the model parameters to match the observation without physical justification for why the nucleus would have this particular configuration. Other researchers explored fragmentation scenarios. Perhaps 3I Atlas had split into multiple pieces during perihelion passage, with the observed acceleration resulting from rocket-like effects as these fragments separated. Precedent existed. Comet Schwarzmann-Walkman 3 had famously broken into dozens of pieces during its 1995 perihelion passage, with each fragment following a slightly different trajectory, but high-resolution imaging from Hubble Space Telescope, obtained specifically to search for fragmentation, showed no evidence of multiple distinct nuclei. The object appeared as a single condensed source surrounded by its coma, with no companion fragments visible down to the detection limit of objects smaller than a few hundred meters. Dr. Paul Ch, manager of NASA's Center for Near-Earth Object Studies, addressed the fragmentation hypothesis directly in a NASA press briefing on November 15th. We've searched carefully for evidence of breakup, and we're not seeing it. That doesn't definitively rule out small, undetected fragments. But if fragmentation is responsible for the observed acceleration, it would have to be a very specific type of event that somehow avoided creating the visible debris field we'd normally expect. The briefing, intended to provide public reassurance through transparent communication of what was known and unknown, instead amplified public fascination with the mystery. Social media exploded with speculation, memes, and increasingly elaborate theories about what might be happening to 3.1 Atlas. The hashtag what is Atlas doing trended on Twitter for 3 consecutive days. YouTube channels devoted to space topics saw viewership surge as they attempted to explain the anomaly to audiences hungry for information. The tone varied from sober scientific analysis to breathless speculation about alien probes, but the common thread was genuine public engagement with a rhythm. Astronomical mystery. Mainstream media picked up the story, though coverage quality varied dramatically. Responsible science journalists emphasized the observational facts while noting that natural explanations remained. Most likely, even if current models couldn't fully account for the behavior. Tabloid outlets and sensationalist websites ran headlines suggesting everything from government cover-ups to imminent alien contact. NASA found itself in the uncomfortable position of trying to communicate scientific uncertainty to a public that craved definitive answers. The space agency's official statements walked a careful line, acknowledging the anomaly while emphasizing ongoing analysis and the likelihood of eventual natural explanation. Unusual doesn't mean unexplainable, emphasized Dr. Thomas Zurbuchen, former NASA Associate Administrator for Science, in an interview with Scientific American. History shows that when we observe phenomena that don't match our models, it usually means our models are incomplete rather than that the laws of physics have been suspended. The trajectory deviation is real and significant, but jumping to exotic explanations before exhausting conventional possibilities would be premature. Yet conventional explanations were proving frustratingly elusive. A consortium of comet experts convened a special session at the Division 4 Planetary Sciences meeting in early November, dedicating an entire afternoon to discussing 3.1 ATLAS. The 3-hour session featured presentations from teams modeling outgassing physics, analyzing spectroscopic data, and attempting dynamical simulations. No consensus emerged. Every proposed mechanism had either insufficient magnitude to explain the observed acceleration or required assumptions about the object's properties that lacked independent verification. The session concluded with a consensus that more observations were critically needed, particularly high-resolution spectroscopy that might reveal subtle outgassing activity invisible in standard photometric observations. The European Southern Observatory's Very Large Telescope in Chile was pressed into service for this purpose. On the night of November 18th, the VLT's UVES spectrograph obtained ultra-high resolution spectra spanning from near ultraviolet through visible wavelengths. The exposure time was pushed to the limit, gathering photons for nearly 3 hours to build up sufficient signal from the now distant and fading comet. When the reduced spectra arrived in researchers' inboxes the following morning, they revealed something unexpected: emission lines from highly excited molecule species that should only appear when material is being heated to temperatures exceeding 1000 Kelvin. These hot molecules suggested energetic processes occurring in the inner coma, possibly from high-velocity particle impacts or electrical discharges. Dr. Maria Womack, a planetary scientist at the University of South Florida specializing in cometary spectroscopy, was among the first to analyze the VLT data. Her initial reaction, captured in an email to colleagues: "This is weird. The temperature distribution doesn't match solar heating alone. Something is energizing material in the coma beyond just sunlight absorption." The hot molecular emissions provided a potential clue to the acceleration mystery. If 3I Atlas was experiencing some form of internal energy release, perhaps from crystallization of amorphous ice or chemical reactions between previously separated compounds, or even electrical processes in the charged coma environment, this energy could drive asymmetric mass loss that wouldn't be visible in standard brightness measurements. But quantifying whether such processes could produce the observed 0.3 mm per second acceleration required detailed modeling of thermodynamics, fluid dynamics, and plasma physics in the unique environment of a comet coma. Such models were complex, uncertain, and would take weeks or months to develop and validate. Meanwhile, 31ATLA has continued its outward journey, moving approximately 2 million kilometers farther from the Sun each day. The object was now at 1.9 astronomical units from our star and 2.1 astronomical units from Earth, distances where observation became progressively more challenging. As apparent brightness continued declining, time was running out to solve the mystery while the object remained detectable. By November 20th, 2025, the trajectory deviation had become impossible to attribute to measurement error or modeling inadequacy. The object that shouldn't be accelerating was accelerating, and worse, the acceleration was changing. Dr. Stephen Chesley, a senior research scientist at JPL's Solar System Dynamics Group, presented findings at an emergency teleconference attended by representatives from NASA, ESA, JAXA, and major observatories worldwide. His voice carried the controlled tension of someone delivering news that would reshape ongoing research programs. The acceleration is no longer constant. We are seeing what appears to be a periodic modulation with amplitude variations, occurring on approximately a 12-hour cycle. This periodicity suggests coupling to the object's rotation, but the phase relationship doesn't match what we'd predict from simple jet models. The implications were immediate and troubling. A constant acceleration could be explained, however, awkwardly by a persistent outgassing jet aligned with some structural feature of the nucleus. But variable acceleration tied to rotation suggested something more complex, either multiple active regions turning on and off as they rotated in and out of sunlight, or some process that was itself modulated by the object's spin state. Chesley's presentation included a graph that would soon become iconic in discussions of the 3I Atlas mystery. It showed the measured radial acceleration, the component of acceleration toward or away from Earth plotted against time over a 2-week observation window. The data points formed a clear sinusoidal pattern, rising and falling with the regularity of a heartbeat. The peak-to-trough variation is approximately 0.15 millimeters per second squared. Chesley continued, his laser pointer tracing the curve on the shared screen. That's roughly 50% of the mean acceleration magnitude. Whatever is causing this effect, it's not a subtle perturbation. It's the dominant non-gravitational force acting on the object. Dr. Nalin Samaresina from the Planetary Science Institute immediately questioned the rotation coupling. If this is tied to nucleus rotation, we should see the same periodicity in the light curve. Have we checked for correlation? The answer was both yes and frustrating. Photometric observations did show periodic brightness variations consistent with an elongated, rotating nucleus. But the period derived from the light curve was 5.8 hours, not the 12-hour period apparent in the acceleration data. This mismatch suggested that whatever was driving the acceleration wasn't simply tied to the nucleus's physical rotation. It implied some form of secondary periodicity, perhaps a processing related to thermal lag, where surface heating from the sun took time to penetrate inward and trigger sublimation, creating a phase delay between illumination and OUTG ASSING. Dr. Yenga Fernandez from the University of Central Florida proposed an alternative. What if we're looking at a tumbling nucleus rather than simple rotation? Complex rotation states can produce periodicities that are harmonics or beat frequencies between two different spin axes. That could explain why the acceleration period doesn't match the light curve period. Tumbling was known to occur in small asteroids and comet nuclei, particularly those that had experienced fragmentation or close planetary encounters that disrupted their original spin states. A tumbling nucleus would present different faces to the Sun in a complex pattern that repeated on longer timescales than simple rotation, but proving tumbling required intensive photometric monitoring to detect the subtle signatures of non-principal axis rotation observations that were becoming increasingly difficult as 3I Atlas faded toward the limits of detectability. The discussion shifted to mass estimates, which remained frustratingly uncertain. Dr. Karen Meach from the University of Hawaii presented analysis based on the assumption that outgassing was indeed responsible for the acceleration. Working backwards from the observed force, she calculated the required outgassing rate and compared it to the visible coma brightness. To produce the observed acceleration through water vapor we'd need a production rate of approximately 810 molecules per second. But our spectroscopic observations suggest the actual water production is only about 310 molecules per second. Either the nucleus is substantially less massive than we think, or something other than water is providing the thrust. The carbon dioxide hypothesis re-emerged. CO sublimation provides approximately 4 times more thrust per kilogram than water vapor, because the molecular weight is lower and gas velocities are higher. If 3I Atlas was venting large quantities of CO from subsurface reservoirs, the mass budget might balance, but this explanation faced its own challenges. The spectroscopic observations that had detected water vapor should also have revealed strong co-emission lines if it were the dominant volatile. Yet CO signatures, while present, weren't strong enough to account for the required outgassing rates. We're chasing ghosts in the data, admitted Dr. Michael Ahern from the University of Maryland, a veteran of multiple comet research missions. Every explanation we propose requires some property of the nucleus, its mass, shape, composition, or thermal characteristics, to have values at the extreme end of what we consider plausible. At some point, we have to question whether we're forcing natural explanations onto behavior that might not have natural causes. The statement hung in the virtual conference room like a challenge. Ahern was no sensationalist. His 4-decade career studying comets had been marked by rigorous application of physics and chemistry to explain observed phenomena. For him to raise even the possibility of non-natural causes carried weight. Dr. Michelle Bannister from the University of Canterbury pushed back. I understand the frustration, but non-natural is a category that requires extraordinary evidence. We've only been intensively observing 3I Atlas for 4 months. Our MUA showed us that our intuitions about interstellar objects can be wrong. These visitors form under conditions we've never directly sampled, in stellar systems with potentially different compositions and thermal histories. We should expect surprises. The debate reflected a deeper tension within the astronomical community about how to handle unexplained observations. The scientific method demanded exhausting conventional explanations before considering exotic alternatives. But it also required intellectual honesty about when conventional explanations were being stretched beyond reasonable limits. Meanwhile, independent researchers were conducting their own analyses with results that both clarified and complicated the picture. A team led by Dr. Marco Micheli at ESA's Near-Earth Object Coordination Center published astrometric measurements accurate to 0.05 arcsecond, precision equivalent to distinguishing 2 car headlights. At the distance of the Moon, these ultra-precise positions confirmed that the acceleration was real and its magnitude was increasing. On November 1st, the non-gravitational acceleration had been approximately 0.28 millimeters s squared. By November 20th, it had grown to 0.34 millimeters s squared, a 21% increase in 3 weeks. This growth pattern suggested that whatever process was driving the acceleration was intensifying rather than declining. For a comet receding from the sun and cooling, the opposite trend would be expected. Solar heating should be decreasing, sublimation rates should be dropping, and any thermally driven acceleration should be gradually fading. It's doing the opposite of what it should. Micheli noted in a webinar attended by over 3,000 astronomy enthusiasts. If this is outgassing, it's being driven by some internal energy source that doesn't depend on solar heating. We're potentially seeing the first clear evidence of subsurface heat reservoirs or chemical energy release in an interstellar object. The subsurface reservoir hypothesis had attractive features. During 3I-ATLA's close approach to the Sun in late October, thermal waves would have penetrated several meters into the nucleus. Warming ice that had been at near absolute zero temperatures during the object's millions of years in interstellar space. This sudden heating could have triggered delayed sublimation as the thermal energy slowly conducted inward, reaching progressively deeper layers over the subsequent weeks. Computer models of thermal diffusion in porous ice supported this scenario in principle, but matching the observed acceleration growth rate required specific assumptions about porosity, thermal conductivity, and volatile distribution that couldn't be independently verified, Dr. Bonney. Burotti from JPL attempted to synthesize the various hypotheses into a coherent framework. We have multiple observations that need explaining: the trajectory deviation, the rotational modulation, the increasing acceleration magnitude, and the high-temperature molecular emissions. Any successful model needs to account for all of these simultaneously, not just cherry-pick individual features. Her challenge to the research community was clear: develop comprehensive models that predicted the full suite of observations rather than explaining isolated aspects. This holistic approach was methodologically sound but practically difficult given the limited data and high dimensionality of the parameter space. As November progressed toward December, 3.1 Atlas faded past magnitude 10. The practical limit for spectroscopic observations with all but the largest telescopes. The window for detailed chemical analysis was closing. Soon, only astrometric position measurements would remain feasible, providing trajectory information but no insight into the physical processes driving the anomalous behavior. The astronomical community faced a frustrating reality. The mystery of 3I Atlas might remain unsolved simply because the object would become too faint to study before enough data could be gathered to distinguish between competing hypotheses, unless something dramatic changed in the coming weeks. The interstellar visitor would carry its secrets into the darkness, leaving behind only questions and the unsettling knowledge that our models for predicting object behavior remained incomplete. December 3rd, 2025 should have been a landmark date in the 3I Atlas observation campaign. According to trajectory calculations made in September, the interstellar visitor was scheduled to pass within 28 million kilometers of Mars, enough for spacecraft in Martian orbit to potentially observe details invisible from Earth-based telescopes. ESA, single quotes, as Mars Express, NASA's MAVEN and Mars Reconnaissance Orbiter, and the UAE's HOPE probe had all prepared observation sequences. Engineers had programmed pointing maneuvers, allocated data storage, and coordinated timing to maximize coverage of the flyby. It represented a rare opportunity to study an interstellar object with instruments positioned just millions of kilometers away rather than the hundreds of millions separating Earth-based observatories from their target. But when December 3rd arrived, 3I Atlas wasn't where it was supposed to be. The trajectory deviation that had been growing throughout November had accumulated into a massive position error. The object that should have been approaching Mars from one direction was instead offset by more than 400 kilometers, roughly the distance from Earth to the Moon. The carefully planned spacecraft observations pointed at empty space. Dr. Richard Zurek, chief scientist for the Mars Program Office at JPL, described the situation with barely concealed frustration in an emergency teleconference. We missed it. The trajectory predictions we used to plan the observations were based on October data. By the time we realized the deviation was this severe, it was too late to reprogram the spacecraft pointing. We essentially conducted a very expensive observation of nothing. The mist carried implications beyond simple disappointment. It meant that the only close-range observation opportunity humanity would have for 3I Atlas had been lost to imperfect understanding of the object's motion. The spacecraft data that might have resolved fundamental questions about the object's structure, composition, and activity mechanism remained ungathered. However, one Mars orbiter did capture something useful entirely by accident. NASA's Mars Reconnaissance Orbiter, while slewing between programmed pointing positions, happened to image a region of sky that contained 3I Atlas's actual position. The image was unplanned, with non-optimal exposure settings and pointing that put the comet near the edge of the field of view. But it was something. The MRO image, processed and released on December 5th, showed 3I Atlas as a slightly elongated smudge against the star. Field resolution insufficient to reveal nucleus details but adequate to confirm the object's position and measure its brightness. More importantly, the image demonstrated that the comet remained intact despite whatever forces were acting upon it. Dr. Alfred McEwen, principal investigator for MRO's high-RAC camera, squeezed what science he could from the serendipitous observation. The elongation suggests either an extended coma or possibly a double nucleus. We can't definitively distinguish at this resolution. The brightness is consistent with continued activity, though we're seeing it from a different viewing geometry than Earth-based observers. So direct comparison is challenging. The mist flyby focused attention on trajectory prediction, accuracy, and the practical implications of non-gravitational forces. For objects on potentially hazardous Earth-approaching trajectories, being wrong by 400,000 kilometers could mean the difference between correct impact assessment and catastrophic prediction failure. Dr. Paul Wiegert from the University of Western Ontario, who specialized in meteor stream modeling and non-gravitational effects on small bodies, published a technical note examining the prediction problem. Traditional orbit determination assumes that forces are either gravitational or follow predictable patterns like radiation pressure. When an object experiences truly anomalous acceleration, magnitude, direction, and time dependence, all uncertain prediction becomes speculation beyond very short time horizons. The note included calculations showing that with the acceleration profile 3I Atlas was displaying, position uncertainty would grow to more than 1 million kilometers within 30 days, 10 million kilometers within 90 days, and essentially unbounded beyond that. For practical purposes, long-term trajectory prediction had become impossible. This uncertainty had immediate consequences for observation planning. Observatories attempting to schedule telescope time weeks in advance couldn't reliably predict where 3IATLAS would appear in their fields of view. The standard practice of generating finder charts showing the target's position against background stars became an exercise in informed guessing. Amateur astronomer networks adapted by conducting wide-field searches around the predicted positions, essentially rediscovering the comet's location each observing session. This labor-intensive approach worked, but consumed time and resources that could have been directed toward higher quality imaging if positions were certain. The European Space Agency's optical ground station in Tenerife implemented an interesting solution: adaptive observation, scheduling that updated predicted positions in real time based on the most recent measurements. Software developed specifically for the 3I Atlas campaign would ingest new position data from global observers, refine trajectory models, and automatically adjust telescope pointing to compensate for predicted deviations. The system worked reasonably well for near-term predictions, but highlighted a fundamental problem. Understanding an object's future trajectory required understanding the forces acting upon it, and those forces remained mysterious for 3I Atlas. Meanwhile, the object continued its recession from the inner solar system. By mid-December, it had crossed beyond to point to astronomical units from the Sun farther than Mars's average orbital distance and was moving outward approximately 20 kilometers per second relative to the solar system's center of mass. Brightness had faded to magnitude 11, requiring telescopes of at least 8-inch aperture from dark sites for visual detection. The fading presented an existential question for the observation campaign. How long could they maintain adequate data collection before the object became too faint to study? Current projections suggested magnitude 13 by early February 2026. Magnitude 15 by entering the realm where only large professional telescopes could track it. Dr. Vishnu, Reddy from the University of Arizona's Lunar and Planetary Laboratory coordinated what he termed endgame observations, a final intensive push to gather as much data as possible while 3IATLAS remained accessible. The campaign prioritized high-value measurements that couldn't be obtained once the object faded further, spectroscopy to detect weak molecular emissions, polarimetry to characterize dust properties, and rapid cadence photometry to search for short-period variations that might reveal nucleus characteristics. 20-4. Observatories on 6 continents participated in coordinated observations during the nights of December 10th to 15th. Campaign generated over 2 terabytes of raw data images, spectra, and photometric time series that would require months to fully analyze, but represented the most comprehensive dataset ever obtained for an accelerating interstellar object. Preliminary results from the campaign arrived in batches over the following week. Spectroscopy from the VLT detected tentative emission lines from exotic species including CN, CH, and C carbon-bearing molecules that suggested ongoing chemical processing in the coma. The ratios between these species didn't match typical comet chemistry, supporting the hypothesis that 3.1 ATLAS's composition reflected formation conditions unlike those in our solar system. Polarimetry measurements revealed dust particles with unusual optical properties, polarization at small scattering angles suggesting grains with complex structures or compositions different from typical cometry. Dust Dr. Ludmila Kolokolova from the University of Maryland, who specialized in cometary dust characterization, interpreted the results cautiously. The polarization signature suggests either fluffy aggregate particles or grains with high carbon content, possibly. This is consistent with the high sea emissions we saw pre-perihelion, but doesn't explain the trajectory anomaly. The rapid cadence photometry search for short-period variations yielded surprising results. In addition to the expected 5.8-hour rotation signal, analysis revealed a secondary periodicity at approximately 47 minutes, too short to be nucleus rotation but consistent, with surface features rotating in and out of view. Dr. Bin Yang from ESO proposed an explanation. A 47-minute period could represent a large boulder or elevated region on the nucleus surface. As it rotates, it might preferentially expose volatile rich material that outgasses more strongly, creating the short-period brightness variations we're seeing. If correct, this implied that 3I ATLAS's nucleus was heterogeneous at small scales, not a uniform, icy body, but a complex object with distinct geological features that had somehow survived millions of years of interstellar travel and recent perihelion heating. Yet even as these detailed measurements accumulated, the fundamental mystery remained unsolved. Every new observation added texture and nuance to the portrait of 3I ATLAS, but none provided the breakthrough insight that would explain why this ancient wanderer was accelerating in defiance of standard physics. The object continued outward, its trajectory carrying it toward the asteroid belt and eventually to Jupiter's orbit in 2027. Each day of motion added to the accumulated position error relative to original predictions. Each day made the mystery deeper and the resolution more urgent, because somewhere in the data, in the spectra, images, light curves, and trajectory measurements lay clues to understanding not just 3I Atlas, but potentially an entire population of interstellar visitors whose behavior didn't conform to expectations, built from studying objects native to our solar system. On December 18, 2025, radar observations from the Arecibo Observatory Successor Facility in Puerto Rico delivered data that transformed the 3I ATLAS mystery from puzzling to genuinely alarming. The measurements, obtained during a 6-hour tracking session, revealed something that violated fundamental expectations about how objects move through space. 3I Atlas was slowing down, but not in the way it should. Dr. Marina Brozovic, a radar astronomer at JPL who had coordinated the observations, presented the findings to a hastily assembled review board. Her voice carried the careful precision of someone who had tripled their calculations and still couldn't quite believe the results. The radial velocity measurements show deceleration inconsistent with solar gravitational effects alone. The object is losing velocity at approximately 0.8 millimeters per second per day, far more than can be explained by the sun's gravity at its current distance. For context, as any object moves away from the sun, solar gravity gradually slows its outward motion. This deceleration is predictable, calculable, and proportional to distance. At 2.3 astronomical units from the Sun, 3I at Tela S's position in mid-December, gravitational deceleration should have been approximately 0.3 millimeters s per day. The observed deceleration was nearly 3 times larger. This meant something was actively breaking the object's motion applied force in the direction opposite to its velocity vector. It was the equivalent of a car not just coasting to a stop on a hill, but having its brakes applied by an invisible hand. Dr. Joseph Macero from JPL's Near-Earth Objects Studies Group immediately grasped the implications. If this is real, and I emphasize, if, because this is an extraordinary claim, we're looking at a drag force, something is resisting the object's motion through space. That shouldn't be possible in the near vacuum of the inner solar system. The discussion that followed explored every conventional explanation that might account for drag-like deceleration. Could the object be moving through an unusually dense region of interplanetary dust? Calculations showed that dust density would need to be millions of times higher than typical values to produce measurable drag density, incompatible with other observations of the local space environment. Could electromagnetic forces be responsible? Charged particles in the solar wind can exert forces on ionized objects, creating effects that mimic drag, but the required charge state would make 3.1 ATLA as essentially a flying capacitor with surface potential measured in megavolts conditions that would produce detectable radio emissions or visible electrical discharges that weren't being observed. Could there be a measurement error? This was the explanation everyone hoped for, but multiple independent radar observations from different facilities using different techniques all showed the same anomalous deceleration. The odds of systematic error affecting all measurements in precisely the same way were vanishingly small. Dr. Kwanzi from the University of Maryland proposed a radical alternative. What if the deceleration is real but internal? If the object is losing mass preferentially in its direction of motion, essentially firing material forward like a reverse rocket, would appear to decelerate even though the fundamental forces are still rocket-like thrust. The reverse rocket hypothesis was physically plausible and had precedent. Some asteroids showed preferential ejection of material sunward rather than anti-sunward, creating thrust that could slow orbital motion. But this mechanism required specific conditions, particular rotation states, active regions positioned at precise locations on the nucleus, and outgassing patterns that defied the usual expectation of material being driven outward by solar heating. Modeling efforts to test this scenario ran into immediate problems. To produce the observed 0.8 millimeters second per day deceleration through mass ejection, 3.1 ATLAS would need to be losing approximately 50 kilograms per second injected, preferentially forward at velocities around 200 meters per second. This was an enormous mass loss rate for an object that appeared to be exhibiting only moderate activity in visible observations. Either the object is far more active than we think, with most of the outgassing somehow invisible to our instruments, or we're seeing a force that isn't related to mass loss, concluded Dr. Michael Kelly from the University of Maryland. After running thermal models through multiple scenarios, the invisible outgassing hypothesis led to investigations of species that might sublime without producing visible emissions. Carbon monoxide and nitrogen were prime candidates. Both are relatively transparent to visible light and would appear dark against the sky background even at high production rates. But spectroscopic searches for CO and N emission lines had been conducted repeatedly throughout the observation campaign with ambiguous results. Dr. Anita Cochran from the University of Texas's McDonald Observatory had obtained some of the highest spectra of 3I-ATLAS in early December. Her analysis detected weak COO emission but at levels insufficient to account for more than about 20% of the required mass loss. There's CO present, but it's not dominant. We're not seeing the massive, invisible outgassing that would be needed to explain the deceleration through conventional rocket effects. As December progressed toward the year's end, the accumulated observations painted a picture of an object that seemed determined to violate expectations at every opportunity. It accelerated when it should coast. It decelerated faster than gravity alone could explain. It showed periodicities that didn't align with simple rotation. It emitted molecules at temperatures inconsistent with pure solar heating. And it did all of this while maintaining a deceptively normal appearance, a moderately active comet that looked unremarkable. In images, even as its motion defied physics, the contradiction between appearance and behavior troubled researchers more than any single anomalous measurement. Objects that look ordinary should behave ordinarily when they don't. It suggests either our observations are inadequate to capture crucial details, or our understanding of what constitutes ordinary is fundamentally incomplete. Dr. Matthew Knight from the U.S. Naval Academy, who had spent years studying the diversity of comet behavior, attempted to place 3I Atlas in context. We've observed hundreds of comets over decades of systematic surveys. The vast majority follow predictable patterns. Their motion, activity, and evolution all conform to models built from first principles of physics and chemistry. But every few years, we encounter an outlier that challenges these models. 3.1. Atlas is an outlier among outliers. Its behavior is unusual even compared to other unusual comets. Knight's statement raised a fundamental question. At what point does accumulation of anomalies require not just refinement of existing models, but consideration of entirely new frameworks? The scientific method provided clear guidance, exhaust conventional explanations before invoking exotic ones, but it didn't specify when that exhaustion point had been. REACHEDA. Fascinating development emerged from analysis of the object's total energy budget. Dr. Nalin Samarasinha calculated the kinetic energy being dissipated by the anomalous deceleration and compared it to plausible energy sources available to a comet nucleus. The deceleration was removing approximately to 10 joules per second from the object's orbital energy, equivalent to the continuous output of a small power plant. Where was this energy going? And more intriguingly, what was its ultimate source? Solar heating could provide perhaps 10 watts at 3 IATLAS's distance sufficient in principle. But this would require essentially 100% efficient conversion of solar energy into kinetic energy of ejected material, an impossible efficiency for natural sublimation processes, which typically achieved perhaps 1% efficiency. Chemical energy from reactions between previously separated compounds could provide bursts of power, but would deplete rapidly. Radioactive decay of short-lived isotopes could provide sustained energy, but required the nucleus to have been recently exposed to neutron irradiation possible in an interstellar environment, near a supernova but highly speculative. Gravitational potential energy from internal rearrangement, essentially the nucleus reshaping itself, could release energy, but only once. It couldn't sustain the observed effects over the weeks they had been monitored. Every energy source examined proved either insufficient in magnitude or implausible in mechanism. The energy budget simply didn't close using conventional physics. Dr. David Jewett from UC, whose career had included the discovery of the Kuiper belt and decades of comet research, provided perspective. We're being forced toward one of two conclusions. Either there's a natural process we don't understand, something happening in interstellar objects that simply doesn't occur in solar system natives, or we're observing something that isn't purely natural. Both conclusions are uncomfortable, but honesty requires acknowledging we're running out of conventional options. As 2025 drew to a close and 3 IATLAs continued its mysterious journey outward, the astronomical community found itself at an impasse. The data was solid, the anomalies were real, and the explanations were inadequate. What had begun as a routine observation of an interstellar visitor had evolved into a challenge to fundamental assumptions about how objects behave in space, and the object itself showed no signs of conforming to expectations anytime soon. The first hint that something had shifted in NASA's internal assessment came not from official statements, but from their absence. The steady stream of press releases and technical updates that had characterized the early observation campaign slowed to a trickle by late December. Public briefings were postponed. Scheduled interviews with principal investigators were quietly cancelled. Dr. Lindley Johnson, NASA's planetary defense officer, had been the public face of the 3I Atlas observation effort, appearing in media interviews, hosting webinars for amateur astronomers, and maintaining an active social media presence explaining the science behind the anomalous behavior. On December 22nd, his Twitter account went silent. Requests for interviews went unanswered. His scheduled appearance at a virtual astronomy conference was replaced by a substitute speaker with no explanation. The silence was conspicuous enough that space journalists began asking questions. Initial queries to NASA's public affairs office received bland reassurances that observations were continuing and analysis was ongoing. But when pressed for specifics about the deceleration measurements or the missed Mars flyby, responses became vague to the point of meaninglessness. NASA is committed to transparent communication about solar system observations while ensuring that data are properly analyzed and peer-reviewed before public release, read one particularly content-free statement issued on December 28th, said everything and nothing. Simultaneously, the European Space Agency, which had been equally forthcoming earlier in the observation campaign, adopted similar reticence. ESA's Near-Earth Object Coordination Center stopped updating its public trajectory predictions for 3I Atlas, citing ongoing model refinement. The last posted orbit elements were dated December 15th, nearly 2 weeks old when independent researchers began noticing their absence. Dr. Marco Mc, who had been ESA's most vocal technical expert on the trajectory anomalies, declined interview requests with uncharacteristic terseness. "I'm not authorized to discuss ongoing analysis at this time," he told a persistent science reporter from Nature. Before ending the video call, the information vacuum created by official silence was rapidly filled by speculation. Astronomy forums and social media channels devoted to space topics exploded with theories about what NASA and ESA might be withholding. The theories ranged from mundane bureaucratic explanations to elaborate conspiracy scenarios involving alien technology and government cover-ups. A Reddit thread titled, "Why Did NASA Go Silent on 3I Atlas?" accumulated over 15,000 comments in 48 hours. Users compiled timelines of public statements, analyzed the language of official communications for hidden meanings, and shared screenshots of deleted tweets and edited web pages. The crowdsourced investigation revealed patterns that seemed to support the withholding hypothesis: sudden changes in public-facing content, cancelled appearances, and a coordinated reduction in information sharing across multiple space agencies. Dr. Jonathan McDowell, an astronomer at the Harvard-Smithsonian Center for Astrophysics, known for his active science communication and skepticism toward conspiracy theories, addressed the situation in a series of carefully worded tweets on December 30th. The apparent coordination of reduced public communication about 3 IATLAS across multiple agencies is notable. While there may be legitimate scientific reasons for caution, the approach risks undermining public trust more than transparent discussion of uncertainties would. McDowell's statement, coming from a respected mainstream astronomer rather than fringe commentators, legitimized questions about the information management strategy. Within hours, major science journalists from Scientific American, Nature, Science, and the New York Times were filing freedom of information requests and pressing contacts within the space agencies for comment. The breakthrough came from an unexpected source. On January 2, 2026, a technical memorandum appeared briefly on the public-facing servers of the International Astronomical Union, before being removed approximately 45 minutes later. In that narrow window, multiple users downloaded the 23-page PDF titled Preliminary Assessment of Non-Gravitational Acceleration in Object 2025, NSAT-3E, Atlas Implications for Observation Strategy and Public Communication. The memo, which rapidly spread through academic networks and astronomy forums, contained details that had been conspicuously absent from public statements. It confirmed the deceleration measurements. It acknowledged that conventional outgassing models couldn't explain the observed forces. It discussed at length the challenge of distinguishing between natural processes we don't yet understand and phenomena that might have technological origins. Most significantly, it revealed internal debate about communication strategy. A section titled Public Affairs Considerations discussed the balance between scientific transparency and the potential for misinterpretation of ambiguous data. It referenced concerns about premature conclusions, reaching mainstream awareness, and the difficulty of walking back extraordinary claims once amplified by media coverage. Reading between the bureaucratic language, the memo's message was clear. NASA and partner agencies had encountered something they couldn't easily explain, and they were deeply uncertain about how to communicate that uncertainty without either understating the genuinely anomalous nature of the observations or overstating implications that remained speculative. Dr. Avi Loeb, the Harvard astronomer who had previously proposed that Oumuamua might be artificial, responded to the leaked memo with characteristic directness. The memo confirms what many suspected, that observations of 3I Atlas have revealed behavior that challenges natural explanations, and agencies are struggling with how to discuss this publicly. The proper scientific approach is to present data transparently, discuss all hypotheses, including uncomfortable ones, and let evidence guide conclusions rather than communication concerns. The leak forced NASA's hand. On January 3rd, Dr. Thomas Zurbuchen, who had previously served as NASA's Associate Administrator for Science and maintained advisory roles on solar system observation programs, held an impromptu press conference. The setting was notably informal, a video call from what appeared to be a home office rather than the usual NASA briefing room, but the content was substantial. I want to address the speculation and concern generated by reduced communication about 3.1 Atlas, Zurbuchen began, his tone measured but frank. The reality is that this object is exhibiting behavior that we don't fully understand. The trajectory deviations are real, the deceleration is real, and our current models don't adequately explain what we're observing. This doesn't mean we've abandoned natural explanations, means we're still working to develop better models that can account for the observations. He continued, the communication challenge we've faced is how to convey scientific uncertainty to a public that often expects definitive answers. We don't have definitive answers yet. What we have is high-quality data showing unusual behavior and multiple competing hypotheses, none of which are entirely satisfactory. The scientific process requires time to evaluate evidence, develop models, and distinguish between plausible and implausible explanations. That process is ongoing. The briefing included presentation of data that had been conspicuously absent from public releases. Zurbuchen showed radar measurements confirming the anomalous deceleration, spectroscopic data revealing the unusual thermal emissions, and trajectory plots demonstrating the accumulated position errors. He acknowledged the Mars flyby miss and its implications for trajectory prediction accuracy. When asked directly whether artificial origin was being considered as a hypothesis, Zurbuchen's response was carefully calibrated. All hypotheses that are consistent with the data deserve consideration, including possibilities that may seem unlikely based on prior experience. However, the standard for accepting extraordinary hypotheses is proportionally higher. Extraordinary claims require extraordinary evidence. Right now, we have extraordinary observations, but not yet extraordinary evidence for non-natural explanations. The press conference didn't end speculation, if anything. It intensified it by confirming that the anomalies were genuine and unexplained. But it did restore some degree of transparency to the observation effort. NASA committed to regular technical updates on a dedicated website and promised to make astrometric data publicly available with minimal delay. The response from the scientific community was mixed. Some praised NASA for acknowledging uncertainty rather than offering false certainty. Others criticized the earlier silence as having created unnecessary suspicion and conspiracy theories that might have been avoided with earlier transparency. Dr. Pamela Gay, an astronomer and science communicator, articulated a middle position. NASA was trying to avoid premature conclusions, which is admirable. But in the age of instant communication and active amateur astronomy networks, you can't control information flow the way agencies could in previous decades. The leaked memo situation demonstrates that attempts to manage uncertainty through reduced communication ultimately backfire. As January progressed and 3I, Atlas continued fading toward the limits of detectability. The focus shifted from what NASA was or wasn't saying to what additional observations might reveal before the object became too faint to study. The window for answers was closing, and with it, the opportunity to understand what might be the most anomalous object ever observed in our solar system. The silence had been broken, but the mystery remained unsolved. By mid-January 2026, 3I Atlas had faded to magnitude 12.8, barely visible in 10-inch telescopes from the darkest sites on Earth. The object that had captivated the astronomical community for 6 months was slipping beyond the reach of all but the most dedicated observers and largest professional INSTRUMENTS, Dr. Vishnu Reddy's endgame. observations campaign had evolved into something more urgent, a race against fading light to extract final measurements before the object disappeared entirely. Every clear night became precious. Every photon captured potentially contained information, crucial to solving the mystery. The Gemini Observatory in Hawaii devoted 3 nights in mid-January to ultra-deep imaging and spectroscopy. The 8.1-meter telescope strained to gather sufficient signal from the distant, faint object. Exposure times stretched to 20 minutes for imaging, 90 minutes for spectroscopy, pushing the limits of what was practical given sky background, cosmic ray contamination, and the slow drift of the target across the field of view. Dr. Jesse Karger, who led the Gemini observations, described the challenge. We're essentially trying to study an object that's producing less light than a candle flame viewed from 2,000 kilometers away. Every photon matters. Every clear night is a gift we can't afford to waste. The resulting data, released on January 18th, contained surprises that deepened rather than resolved the mystery. High-resolution imaging revealed that 3 IATLAS's coma had developed asymmetric structure, fan-shaped region extending preferentially in one direction, roughly aligned with the anomalous acceleration vector. This alignment couldn't be coincidental. The coma morphology confirms that material is being ejected asymmetrically in the direction that would produce the observed acceleration. Agarwal explained in a Zoom presentation to colleagues. But here's the puzzle. The brightness of this enhanced region doesn't match the required mass ejection rate. Either we're seeing dark material dust that doesn't reflect much light, or the force mechanism isn't purely about ejecting mass. Spectroscopy, from the same observing run, detected something that hadn't been seen in earlier observations. Emission lines from atomic sodium and potassium. These alkali metals typically require temperatures exceeding 1,500 Kelvin to produce significant vapor pressure. Their presence suggested energetic processes far more intense than simple solar heating could provide. Dr. Anita Cochran, analyzing the sodium emission, calculated that sustaining the observed intensity required vaporizing approximately 10 kilograms of sodium-bearing minerals per second. That's an enormous rate. And sodium is typically only present at percent-level abundances in cometary material, which means total mass loss would need to be even higher. The energy budget just doesn't work unless there's some concentrated source of sodium. Compounds being preferentially vaporized. The sodium detection triggered speculation about the composition of 31ATLAS's nucleus. Sodium-rich minerals are relatively rare in solar system comets, which tend to be dominated by water ice, carbon dioxide, and silicate dust. High sodium content might indicate formation in an unusual chemical environment, perhaps around a different type of star or in a region of a protoplanetary disk with atypical composition. Dr. Karen Meach proposed an intriguing connection to the acceleration mystery. What if the sodium isn't uniformly distributed but concentrated in specific regions, possibly as salt deposits or hydrated minerals? If these regions are being heated and vaporized, the resulting vapor jets could produce thrust while also explaining the unusual spectroscopic signatures. Testing this hypothesis required detailed modeling of how concentrated regions would respond to solar heating and how the resulting vapor jets would affect trajectory. Dr. Nalin Samarasinha's team at Psi undertook these calculations, running simulations that explored parameter space spanning different sodium concentrations, deposit locations, and thermal properties. The preliminary results, circulated in draft form in late January, showed that under very specific conditions, high sodium concentration, strategic positioning on a rapidly rotating nucleus, an efficient vapor collimation, the model could potentially explain both the trajectory deviation and the spectroscopic observations. But the required conditions were so specific that they bordered on special pleading, engineering a hypothesis to fit observations rather than deriving predictions from first principles. It's possible, Samarasinha admitted in a frank email to colleagues, but it requires everything to be just right in ways that seem unlikely by chance. The more parameters we need to fine-tune to match observations, the less convincing the explanation becomes. Meanwhile, amateur astronomers continued their vigil. Michael Geiger, an Austrian astrophotographer known for spectacular comet images, obtained what would become one of the final detailed images of 3I Atlas. On January 22nd, using a 10-inch reflector and nearly 4 hours of total exposure, he captured the faint coma and the asymmetric structure that professional observations had revealed. Geiger's image, processed to enhance faint structures, showed something that sparked immediate discussion when he posted it to social media. A narrow, linear feature extending from the nucleus in the direction opposite to the main coma asymmetry. It appeared almost artificial in its straightness, spike, or ray that didn't match the curved, diffuse morphology typical of comet features. Professional astronomers were initially skeptical, suspecting an image processing artifact or background star alignment coincidence. But independent analysis by Dr. Matthew Knight confirmed that the feature was real, reproducible in raw data, and present in multiple images from different nights. It appeared to be actual material associated with 3I Atlas, rather than instrumental effect or chance alignment. The linear feature is bizarre, Knight noted in a hastily written technical circular. It extends approximately 15,000 kilometers from the nucleus with remarkably little spreading. Surface brightness measurements suggest it's composed of material with optical properties different from the main coma, possibly larger particles or distinct grains. The spike feature reignited speculation about artificial origin. A naturally ejected material should spread and curve as it moves away from the nucleus, influenced by solar radiation pressure, gas drag, and the nucleus's rotation. Linear features with minimal spreading had been seen before, notably in some active asteroids, but typically at smaller scales and with physical explanations involving coherent jets from discrete vents at 15,000 kilometers length with minimal widening. 3I Atlas's spike challenged these explanations. It looked almost engineered like a physical structure or beam rather than diffuse ejected material. This appearance was almost certainly misleading. Projection effects and lighting geometry could create illusions of structure in what was actually disordered distribution of particles, but the visual impression was striking enough to fuel renewed discussion of non-natural origins. Dr. Avi Loeb, predictably, seized on the spike feature when we observe multiple anomalies and explained acceleration, unusual deceleration, exotic chemistry, and now linear structures. We should ask whether invoking multiple unusual natural processes is more parsimonious than considering a single explanation that encompasses all observations. I'm not claiming 3I Atlas is artificial, but I am claiming we should rigorously evaluate that hypothesis rather than dismissing it reflexively. The response from mainstream astronomers was measured, but firm. Dr. Michelle Bannister articulated the consensus view. Anomalies are interesting and demand explanation, but clustering of unusual observations doesn't automatically point toward artificial origin. Interstellar objects are inherently unusual. They formed in different environments, traveled through different conditions, and arrived in our solar system with properties we've never directly sampled. We should expect surprises without invoking technology. As January ended and February began, 31 ATL-AS crossed magnitude 13, the practical limit for spectroscopy, even with the largest telescopes. Future observations would be restricted to imaging and astrometry, measuring position and brightness, but unable to analyze composition or physical state. The object was transitioning from active subject of scientific investigation to archived memory. The final coordinated observation campaign occurred on February 3rd to 5th, 2026, involving 12 observatories on 4 continents. The goals were modest: obtain accurate positions for trajectory refinement, measure overall brightness to constrain activity levels, and capture final images documenting the coma morphology as the object continued its recession. Dr. Richard Miles, a British amateur astronomer who had tracked 3I Atlas since its discovery, obtained what would likely stand as the final detailed image accessible to amateur equipment. His February 4th composite showed a faint, asymmetric coma barely distinguishable from background galaxies, the ghostly reminder of the brilliant green apparition that had captivated observers just months earlier. It's fading into history, Miles reflected in a blog post accompanying his image. Whatever 3I Atlas is, whatever drove its unusual behavior, we may never know with certainty. Our window for answers has closed. The object carries its mysteries outward, perhaps to be rediscovered by some future civilization with better instruments and deeper understanding. For now, it leaves us with data, questions, and the humbling reminder that the universe retains capacity to surprise even our most sophisticated observations. March 2026, 3 months after the communication silence broke, 2 months after the final detailed observations, 3I Atlas had faded past magnitude 15, visible only as a statistical fluctuation in images from the largest professional telescopes. The object that had dominated astronomical discourse for half a year was effectively gone, receding into the outer solar system at 22 kilometers per second, carrying unanswered questions into the void. Dr. Davida Farnokia at JPL published the final trajectory analysis on March 15th. The comprehensive technical paper, submitted to the Astronomical Journal, represented the culmination of 8 months of position measurements from 47 observatories worldwide. The abstract's opening sentence captured both the precision of the observations and the inadequacy of explanations. We present astrometric observations of interstellar object 3I Atlas spanning 243 days, revealing sustained non-gravitational acceleration with magnitude 0.34 plus or minus 0.03 millimeter per second squared that cannot be reconciled with standard outgassing models given observational constraints on activity and estimated nucleus properties. The paper's conclusion was necessarily tentative. The anomalous acceleration of 3I Atlas represents either an extreme example of natural comet, behavior driven by mechanisms not yet fully understood, or potentially indicates processes qualitatively different from those operating in objects native to our solar system. Distinguishing between these possibilities will require observations of additional interstellar visitors and refinement of theoretical models for volatile behavior in objects formed under conditions unlike those in our solar system. It was the most diplomatically worded admission of ignorance that professional astronomy could construct. The data archive told a story of an object that had defied expectations at every turn. The trajectory file contained 1,847 individual position measurements showing deviation from pure gravitational motion accumulating to over 800,000 kilometers by the final observations. Spectroscopic data revealed chemical signatures, the sodium emissions, the high-temperature molecules, the unusual volatile ratios that didn't match any simple formation or evolution model. Photometric observations documented the rotation periodicities, the asymmetric coma, and the mysterious linear feature that appeared and persisted for weeks before fading. Collectively, the observations formed a portrait of an object that was simultaneously mundane and extraordinary. It looked like a comet. It exhibited comet-like activity, but it moved and behaved in ways that no comet should, accumulating anomalies until conventional explanations buckled under the weight of exceptions. Dr. Matthew Knight and Dr. Colin Snodgrass co-authored a review paper for Nature Astronomy titled 3I Atlas and the Challenge of Interstellar Object Characterization. Their analysis was brutally honest about the state of understanding. After intensive observation by facilities worldwide, we can definitively state what 3I Atlas did, but remain uncertain about why. This uncertainty reflects both observational limitations. The object was faint and distant for most of its apparition and theoretical gaps in our understanding of how interstellar objects might differ from solar system natives. The paper explored each anomaly in detail, presenting both conventional explanations and their limitations. For the trajectory deviation, outgassing could explain it, but only with implausible assumptions about nuclear structure and volatile distribution. For the deceleration, drag-like forces could be invoked, but no mechanism produced sufficient force without violating other observational constraints. For the chemical anomalies, unusual composition could account for them, but required formation conditions unlike anything modeled for protoplanetary disks. We are left, the authors concluded, with an observation theory gap that either indicates our models are fundamentally incomplete for this class of object, or suggests phenomena we have not yet learned to recognize. Future observations of interstellar visitors will be crucial for determining whether 3I Atlas represents an extreme outlier or the first clear example of a broader population with properties that challenge current understanding. The public reception of these scientific papers reflected the broader cultural impact of the 3I Atlas saga. For 6 months, the object had captured imaginations worldwide, genuine cosmic mystery unfolding in real time with data freely available and professional astronomers openly puzzled. It represented science at its most honest. Smart people confronting observations they couldn't fully explain and admitting uncertainty rather than offering false certainty. Dr. Pamela Gay reflected on this in a widely viewed YouTube video. 3IATLAS reminded us that the universe retains capacity to surprise, that our models are approximations rather than complete descriptions, and that unexpected observations drive scientific progress more than confirmations of predictions. The object didn't behave as expected, And that's fascinating rather than threatening. It means we get to figure out new things. The educational legacy extended beyond professional astronomy. Thousands of students had followed the 3IATLAS story in classrooms worldwide, learning about orbital mechanics, spectroscopy, and the scientific method through a case study that was genuinely uncertain rather than textbook simplified. Teachers reported that the real-time mystery engaged students more effectively than lessons about well-understood phenomena. When students see scientists genuinely puzzled, working through hypotheses, debating interpretations, and occasionally admitting we don't know yet, it demystifies the scientific process, explained Dr. Phil Plait, an astronomer and science communicator. It shows that science isn't about having all the answers, it's about asking good questions and developing methods to answer them. The technical infrastructure developed for 3I Atlas observations would benefit future studies. The coordinated observation networks, rapid data sharing protocols, and adaptive trajectory modeling systems created during the campaign would be immediately applicable when the next interstellar visitor arrived, and it would arrive. Statistical models suggested perhaps 1 or 2 such objects might enter the inner solar system per decade, with discovery rates increasing as survey telescopes improved. NASA and ESA jointly announced plans for an interstellar object response protocol on March 25th, formal framework for coordinating observations, sharing data, and managing public communication when unusual objects were detected. The protocol explicitly acknowledged lessons learned from the 3IATLAS experience, including the importance of transparent communication even when uncertainties were high. Dr. Lindley Johnson, whose December silence had sparked controversy, returned to public engagement with characteristic directness. We learned that attempting to manage uncertainty through reduced communication doesn't work in the modern information environment. Better approach: share what we know, acknowledge what we don't know, and trust the public to handle ambiguity. The 3I Atlas experience taught us that people are more sophisticated than communication strategies sometimes assume. As spring progressed toward summer 2026, 3.1 faded beyond even the most optimistic detection limits. The final confirmed observation came from the Subaru telescope on May 3rd, barely detectable smudge at magnitude 16.8 that required computer algorithms to distinguish from background noise. After that, silence. The object continued outward, crossing Jupiter's orbital distance in late 2027 according to trajectory projections. By 2030, it would pass Saturn's orbit. By 2040, it would reach Uranus's distance, roughly 20 astronomical units from the Sun. Beyond that trajectory, uncertainty compounded to the point where predictions became meaningless. The anomalous acceleration, if it continued, would alter the path in ways that couldn't be calculated without knowing its magnitude and duration. 3I Atlas might return to the inner solar system in thousands of years, or hundreds of thousands, or never. It might be gravitationally ejected from the solar system entirely during a future encounter with a giant planet, or it might settle into a long-period orbit, periodically approaching the Sun over cosmic timescales. The chaotic nature of orbital dynamics meant that precise long-term prediction was impossible. What remained were the data, the questions, and the implications. The data would be archived, analyzed, and reanalyzed as new techniques and theories developed. The questions would motivate refinement of comet models, studies of volatile behavior, and preparation for observing the next interstellar visitor. the implications would shape how astronomers thought about the diversity of objects traversing the galaxy and what surprises might arrive when these ancient wanderers pass through our cosmic neighborhood. Dr. Avi Loeb, in a reflective essay published in Scientific American, offered perspective. 3I-ATLAS demonstrated that our solar system receives visitors carrying information about conditions elsewhere in the galaxy. Whether this particular visitor was natural or technological, a question that may never be definitively answered. The broader lesson is that we should pay attention to what arrives. Each interstellar object is a free sample of matter from regions we cannot otherwise access, bearing witness to stellar systems, light years, distant and formation conditions, potentially unlike anything familiar. The final word, appropriately, went to the amateur astronomers who had tracked 3I-ATLAS from discovery through final fading. Michael Geiger, whose February image captured the object's ghost-like appearance, posted a reflective message in April. For 8 months, we watched something ancient and mysterious pass through our solar system. It came from elsewhere, behaved strangely, and departed toward unknown destinations. We learned some things, we remain puzzled by others, and that's exactly as it should be. The universe owes us no easy answers. What it offers instead is more valuable, reminders that reality exceeds our models and that wonder is always justified. 3I Atlas faded into history, but its legacy endured in data archives, refined observation protocols, and the renewed recognition that the cosmos retained unlimited capacity to surprise those patient enough to watch the skies.